what we're doing here. So we started playing around and trying to invent a language of proofs. And the idea is that we want, like, for each connective here, hopefully there will be enough as primitives, 7 of them. We want to develop a language, and we're on our way there. We were only able to use, like, for each connective, I want to know how to use it in a proof. If I know this, what's good, how can I use it? And if I want to prove it, how can I, like, damage it, attack it, eliminate it, or stuff like that. Forget the word eliminate, sorry. It's like reserved, we'll see why. And actually a bit on Zulip, we made tiny progress, unfortunately. We know now how to attack a disjunction. The idea is that if I want to prove P or Q, the move that I have to decide is go left or go right. If I go left, now my goal is to prove P. If I go right, now my goal is to prove Q, and nothing changes on my givens. So the idea is, with exactly the same inventory of what I have to kill the same thing. I have to kill the part of the thing that I will choose, the left or the right. So there are a lot of things missing here, but quickly I will more or less give the answer. This should have taken place in Zulip. So more or less we know this. Why? Because, because when I was comparing these theorems here, that superficially they look the same, but I hope we're appreciating that there are different things, different games to be played. This one, the goal was for all A, B, C, blah, 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 while this one, the goal was this, and somebody already had introduced some things in our givens. And here, there were a lot of things introduced in our givens, and the goal was just this. So I can more or less imagine that the way to, I should write this. So for the first theorem, I will use this notation. I will introduce it today. I think I haven't used it so far. So the idea is, from all those things, I can infer this, I can prove this, these things entail this. There are various ways to think of this. So the first one, and actually this gives me a way to describe the game board that I'm playing, the givens and the goals, without drawing all this table. So the first one I could summarize like that: for all A, B, C, blah, blah, blah. While the second one would be, if I give you like an int and another int, and C, another int, from these things, these givens, you can infer that A divides B and B divides C implies A divides C. And the third one would be something like, you have even more givens, you have all those integers, and then you also have a proposition, which is this. I'm not saying anything new, I'm just introducing this notation here to describe what's going on, the state of the... Now I'm writing the initial state, but the idea is that each command will do something there. Okay, either on the left-hand side, on the givens, or on the right-hand side, or some commands will do on both. So this would be A divides C. And obviously now, I don't get to say that these things are exactly the same games to be played or the same theorems to be proved. Okay. So if I see what happened, if I compare these two, I can more or less guess that this is the command that I will use to attack the for all, because the for all here was in my goal, and this feels like the first line of proof that this guy would write. So yeah, this is how we will do it. So I will say here, actually I will progress here. Okay, so this is for all. So the command would be, essentially I'm saying, give me an arbitrary, give me some member of, some element of the type alpha, and I have the duty to pick a name. And we can discuss a bit how much liberty I have there. And there is some liberty that is like literal liberty, you can do it, and some things that you cannot do it because I will complain about it, but like your system or whatever you may be talking to will accept it, but I will pay extra attention to picking good names and selecting variables from the correct neighborhood of variables, because there are neighborhoods of variables like names, like ABCs, this is a neighborhood, XYZ, that's a different neighborhood, PQR, that's a different neighborhood. And if you say like ABX, you should have like a reason for doing that. Or if you start from YZW and you skip X, you should have a reason for doing that. And I will emphasize this. Unfortunately, if you try these silly things on Agda, on Lean, or some proof assistant, they will not complain. And even if they invent names for the time being, but I expect this to change in the near future, the names are terrible. They're like X12 or something like that. And you cannot imagine a human be able to reason with a proof when all the variables and the names you're using like X1, X2, X3. This is very weird. So there is some like social human communication aspect to picking the right names, and there is an essential also aspect that Lean and Agda and all those guys will complain about it, and it's use a fresh name. So you cannot say let A be, I will call your integer A if on your scope there is an object also called A. Maybe some systems will permit it, but then what happens is that from now on this A will refer to the new thing, and you don't have any way to refer to the previous thing. So we will avoid this name clashing there, and this is implicit. You don't have a choice here. It has to be an alpha. And I now want suggestions on what this command will do. So I will pick a name here. I have to make a choice. Okay, let's say I picked, I don't know. I will call it A. This supposes that A is not occupied, it's not in my scope, I can call it A, I called it A. And now A refers to, RT, would you please close the door? Thank you so much. And now I am referring to this arbitrary element of type alpha by the name A, okay? So, whether it's arbitrary or not, it's something that we can look at the state and decide. Pretty much, arbitrary means you don't have extra data about it. The only thing you know is its type, it's an element of alpha. So even if you, you just got in and I'm in the middle of a proof, you can see the givens and the goal at this point and say, okay, this is arbitrary, or maybe even furthermore, this is arbitrary with this property, because I only know its type and this property that it has, and I don't know extra stuff. And the moment you assume something, it loses its arbitrariness, okay? So this being arbitrary or not is like a very specific thing. It's not like up to discussion. We can discuss it, but it's not like a matter of opinion or point of view or stuff like that. So ideas of what's the effect here? Like I execute this. My goal was this, okay? Oh, okay, so actually that's wrong. Nobody complained, why? It should be here. This is how I attack it, right? It was my goal to prove for all blah blah. And now I'm attacking the first for all here, and the idea is that, what's the effect? Somebody? Yes?
A outputs pro.
A what? Pro? What? What's the second word?
F of A, that's the goal, no?
Phi. It's not an F, it's a phi. Okay, so you said what will happen in the goal, and yes, the goal will change and it will become phi of A. And what's the other thing that happens? Yes, Lazarus. Yes?
It binds the first universally quantified variable.
If you are looking at the quantifier, you're still looking at the goal, and yes, so you will chop this off, right? You will decapitate this thing. This is pretty much what Sotiris. Yes, Sotiris is saying. And what happens on the givens? Pretty much what you said, but say it again, please.
Introduce a type for the variable with the new name.
Yeah, so in my example, you will get an A of type alpha.
Yes, but don't you also have to rename the variable in the...
Yes, exactly. Okay, so in the givens, I gain an A. In the goals, I'm gaining a new goal. What is the new goal? It's phi of X, but I have to rename all three occurrences of X with A. Okay, so I would write this phi of A. So here, I had made a silly example. It's right here. Okay, so we've seen this happening. So here, if I look first on the first line, remember these are like 3 lines here. The first one is let you int. So I'm getting an int, And the goal, it's not shown here, but the goal is for every b, for all c, and now it will be u divides b, and b divides c implies u divides, what's that, c. Does that make sense? So I need to prove that for every x something happens. I say, give me an arbitrary element, I will call it a, and now I have to prove that for a, that thing happens. This is pretty basic, I hope. Okay, maybe too basic. So quickly, let's see a few more. We have pretty much seen this, it's quite similar, which is suppose, okay, it's right here. So I have not seen how to use these things, and we will see it in progress. So I want actually to continue a little bit of what's going on here and step a bit back and criticize some things. I hope that I will irritate three different groups of you here. All mathematicians, which have a lot, people from algebra, and maybe some things about logic, but we'll see if I will succeed. So let me copy this. We were here, and currently our givens and our goals are these here. Okay. So how should I proceed? I could write something like that, and this is something I want to use to irritate you a bit. So I would say, since u divides v, then, or therefore, I don't know, then there exists k, which is an integer, such that, okay, what does that mean? U times k equals v. Essentially what I'm doing here, it's like I'm looking at this. Somebody else might write, I will try to be fast here, if and all the rest. And maybe to emphasize my point, I should rename this to some other word, like thence or therefore, or we can infer or whatever. I will use thence. Okay. Since u divides thence, there exists blah blah. If blah blah. First of all, thence. Think of it like έπεται, από αυτό έπεται, something like that. It's like hence. Okay. The difference is that hence is like here or this, and thence is like there or that. Okay. So since u divides v, from that thing over there, I can conclude there exists a case such that blah blah. Somebody else might write like this. I want to pay I want to pay attention to these two because they will not be similar. They are completely different. They have even different types. Somebody can tell me the difference. Yes, Manolis, right? Yes.
The first is essentially an inference. I mean, you can
From the names that we have seen so far, what kind of type you would say this is?
command.
Yes, it wants to do something, right? It says, from this thing, I want to infer that. Or, to make it imperative, to sound more like command, from this thing, go and infer that. Okay, while the second one is like a proposition, okay? So, we should not write it in proof. It appears in proofs, in human written proofs all the time, but you understand it. You consider it like command. When you're reading like Euclid geometry, Euclid doesn't say things like, if you draw a circle, if you put the compass on this point and draw and pick a radius of that thing, a circle will be drawn. That's a proposition. Yeah, it will. So what? No, it says put the compass on this and do that. Okay, and something is happening. So this is the command. Okay, so for this reason, we will not write like that. This doesn't make sense. write a random proposition in the middle of instructions, we will write it like the first one. And the idea is that when I write the since P then Q, it means that from P infer Q. Okay? And what would be the second line that we write after this? It would be something like since somebody help me, please. Nobody wants to help me, okay. V divides W, then there exists, or there is, I don't know, there is a, I don't know, K prime, such that such that V times K prime is equal to W. Okay, are we following what's going on? So how do these commands change what's going on here in my state? And would anybody be okay if I delete this? If you haven't noticed, I deleted the prime.
Why delete? No.
So somebody objects to this removal of at least one. Any other people want to join Sotiris? 2, thank you. 3, thank you. So what's the problem? Nobody said it's the same K, right? Okay, but the next question was who wants to object the objection? And it's Manolis and Lazaros. And Lazaros, go ahead. It doesn't have it. Ah, okay, this thing, okay. Was it the same thing you were going to say? Okay, sorry, I left this implicit. Oop. So this is not what I was thinking about. Maybe Manolis has a different objection?
Yeah, I have an objection to the objection, which is that the information we have gained is not the actual K, it's the fact that there exists K.
Yeah, thank you. So what does this thing mean? Let's see, for the student, let's say, or for the person who wrote this in a proof and thinks that it actually made some progress, let's see what happened. What does this mean? If I see the definition of this, and this is why I was insisting in the first class to understand the difference between intension and extension, U divides V means exactly this. There exists a K such that blah, blah, blah. So essentially, this line is saying, since U divides V, then U divides V. If I write it like that, everybody will agree that this did nothing, and yes, technically it's correct. If P, from P I can infer P, but this did absolutely nothing. What it most definitely did not do is introduce an integer here. It's just saying there exists some integer, and we should start paying attention to the scope of variables, because this K here is just a binder here, and it does not live outside this proposition. I could call it whatever I like. And for this reason, it's a very bad idea, actually, to use K line here, because first of all, you show that you don't understand what's going on, and soon you will run out of variables. It's like you're programming, and for every time, for each loop that you use, a for, you use for I, and then on the second time you want to make a loop, you think that you cannot use I again. This I starts living on the first line of this loop. We should understand the scope of the variables. And same thing you have written at some point like an integral. This is maybe more common for like mathematicians, something like ax. I have here like f of t, dt, and then I wanted to do something, mention a second integral, and I say, oh wait, I cannot use t again. I have to use like f t prime or t1. dt1. This is obviously silly, because you understand that this thing is just a binder here. There's no t outside of this thing. Okay, I don't want to get a lot into bound and free variables and stuff like that. Feel free to study this if you're not very sure what I'm mentioning here. But let's say that there is a scope involved, and we should always pay attention for each name that we're using, what's its scope, and where it is visible and where it dies off. Okay? Yes, so,
yes,
question.
But you want to combine variables from each scope in order to prove what you want to prove.
Essentially, you're saying, yes, but this is useless. And I agree. Because this way of writing, we didn't do anything. We just said, if U divides V, then U divide, from this I can infer that U divides V. So I need to do something to obtain actually an integer with this property. So we are reaching this thing here. How do I use the existentials? The enemy, the person I'm trying to convince, is doubting that there exists this thing. Has accepted the existence of certain things. They are in my givens. Okay? So I need a way to use it. How can I take advantage of it? And since we agree that there exists something with a property, I'll say, okay, give me this thing and I will give it a name so I can refer to it. So this is how I will use the exists. I will write here let, and I have to pick a name. Be careful with these names that I will pick, of type alpha. I don't have an option here. And this is the important difference, such that it has this property. So if I use like A here, I'm soliciting, like I'm asking for an object that has this property, such that I don't have an option here. Phi of A. Does that make sense? This is how I will use this. So instead of writing this, I will say, where was it? Okay, let me add the page here. Then let, what's that? I will pick a name. Let K, maybe, or I don't know, A, I will call it A. Let A of type integer, obviously, such that, and what is phi of A here? I'm saying what I'm using this, so I need to look here and substitute.
U times A equals V.
Thank you. So U times A equals V. And now this actually did something, so I'm happy. And similarly, you understand, I have to use the other thing, I will pick a name, and now I have to be careful because I cannot pick the same name. Now you should have the objection that you used to have back then. The real objection in this line is you didn't do anything. You're saying, it's like you're another lawyer saying my client is innocent because my client did not kill the victim. That's what innocent means in this sense. My client is innocent because he's innocent. It's not convincing. Maybe it is because it's psychological, but it's not mathematically, it doesn't make a progress mathematically. Yes, what do you want to say?
It's immersed.
Maybe. Yes, thank you. Okay. Rookie mistake there. So A equals B. Okay? And you understand more or less how this will go. My goal all this time is to prove to show an existential. We have discussed a bit on Zulip. Sorry for the up and down. Okay, I wrote this on the wrong way, in the wrong table. Sorry for that. So this thing should be. Maybe this will work. I don't think I've done this ever. Yes, it worked. Okay, so it's here. This is how to use it. And how do I attack it? So I think it was Areti who was trying to figure this out on Zulip. And the idea was, in order to prove an existential, I have to show a certain object that has this property. So the way we're going to encode this like in commands, it's like I will put a witness on the table and I will say, okay, this is my guy. Obviously, the thing does not stop there, because if you want to prove like that there exists an even prime, maybe you pick 8, but there are further duties that you have to do to finish the proof. Now that you put 8, you have selected your witness, you have to defend that indeed it has this property. So I will maybe use the word use, or wit from witness, I don't know. And I have to pick a certain of my choice, right? Of the correct type. What is the type here? The type is alpha. And what do you think happens in the state of the proof after this? Suggestions? So I want to prove that let's see this concrete example that I'm trying to prove here of number theory. I want to prove that there exists some integer that has this property, and I have to say, okay, valid move would be to say use like, I don't know, 42. I could do that. It compiles. It's a wrong move, okay? I will not manage to finish this proof. But I could do that. And what happens with this command? Somebody? Anybody else? So I'm trying to convince someone that there is a k such that u times k equals w. If I say I will use 42, yes, thank you, Konstantinos. What happens in my goals? What happens in my givens? Where is the change?
Πλέον στα goals θα βγάζουμε το άτομο με το 42.
It's not an alpha, it's a k, and yes. Okay, so if I do that, my goal becomes now to show that u times 42 equals, what was that, w. Okay, I will not manage to do that. It's a bad move, but it's a valid move. Okay, so the idea is, in order to show and to prove an existential, I have to find an object that satisfies this, put it on the table, and then defend that in fact it has this property. There are two things that I have to do, essentially. Okay. Okay, the table is, hopefully we'll finish this today, actually in the next few minutes, not all of it, but the essential part that I need now. Okay, so for the time being, I want to see how this would go here. How would we prove this? Anybody? 42 doesn't work. You might think a bit and do some scratch work and then want to impress your friends and they say, I will actually use, I don't know what it is, like A times B or K times, how did I call these things? A. Okay, probably you realize that it's too soon to figure out what your witness should be because you haven't taken advantage of this guy actually yet, and you need an integer that has this property in order to construct your witness. Okay, so here you should do something like okay, I will call this like B, maybe, such that, and this will be V, and this will be B, and this will be W. And I will keep naming the things I'm gaining in the same fashion I did here, so that I can criticize this because it's important for me. So actually this will be like, let's call this 2. Let's call this 3. And now let's see, what am I using? What is this thing? U divides W is what? It's 2. Am I alone or are you following me? Like, I said here, extract the left part of this guy, which is this. So I'm giving it a label, I'm calling it 2 for some reason. And then extract the right guy and call it 3. And I'm giving it like a name, maybe 3. And you say, why would you give it a name? I don't have to, but you have seen this a lot in proofs. It happens, and I need to talk about it. This is why I'm doing it here, even though it's not so necessary. And such that blah, blah, blah. Okay, so here, I would like a name for this as well. And mathematicians are unable to label things with anything besides numbers. And this is very bad. Every theorem, most of the theorems will be theorem 7.5.2, and within a proof it's 1, 2, 3, 4, 5, 6, while actually you could use some more useful names. And that's the first step we're going to do here. Like maybe here, I don't want to call it 3. Essentially, this is a hypothesis I have about A. Maybe I would like to call it HA. It's just a name. And this would be like something HB. Now, instead of keeping track of, what was it, 7, I have to keep finding what 7 means. I have a much better name for this hypothesis. HA, it's something about A, and HB is something about B. And I could do some similar things early on. I don't want to polish it too much. Are we okay so far? Yeah, okay.
There's a typo at the beginning of the
There's a what, sorry?
A typo at the beginning of the second statement, the last statement. It's V divides W.
Is this line or this one line?
V divided W.
Okay, thank you. Is this one? Thank you. Someone is not sleeping. That's good. Okay, V divides W. And maybe instead of that, I would say from 2 or 3 or whatever, infer that such blah, blah, blah. Okay, so how would I finish this off? I would do something that we usually do, and we'll have to justify it somehow. We'll say like compute or calculate, or I don't know, compute maybe. And what you do, like in the computation table, the things are like you put an object on the table and you start substituting equals for equals on it until you reach something, and then you say, therefore the first thing should be equal to the last thing. So what I could do here, if I don't want to embarrass myself a lot, I could say something like U, no, actually like W maybe, is equal to V times B, and this is equal to V times U times A, and this is equal to, thank you, I have a mistake there. Okay, yes, what's the mistake?
Replace V instead of B.
Yes, so thank you. So actually this should be, I'm testing you and you are not test. UA equals times B, and this should be like something like UAB. And this little, we'll see how we can get it to work actually, but this little thing, you can see it right now as a command that gave me a new data, a new given, which is that the first guy is equal to the last guy. So this will be like W equals U times AB. And so like this in the givens, I will have everything I used to have, but also I'm getting a new equation, sorry, UAB. And now it's finally kind of obvious who my witness should be, and I will say, okay, I will use this guy, use AB. This will be my witness. I could have done that earlier if I want to impress someone. How did he figure this out? I don't need to do that, okay? Use AB, and now my goal is exactly my given, so it's done. I can write something like immediate, or I don't know. This immediate, I will not bother with it. I will consider that anytime I draw this tombstone, if my goal is in my givens, I have the right to finish a proof. I managed to get what I needed. So more or less, is this followable by you? Okay. So yeah, what's?
Yeah, it's not clear how you find the witnesses. You have these existential statements, but
You have a divine inspiration. If you put this line here, it looks like a divine inspiration. Here, what you are asking is like, how can we think of what we should do? In this case, it's not so difficult because if you look at the thing you want to prove, like it's you want to find that.
no, I mean you have no way. You have not declared how to compute A and B. So
This part here, I haven't mentioned it. Why? Because actually this part has to do with equality. And pretty much I haven't said anything about it yet. But the idea is that I should be able to do this calculation. But for each step, I forgot to mention this, and I wanted to mention this. For each step, I have to justify it by saying why, what permits me to substitute something with its equal. In other words, why are they equal? So here, I will write the justifications in square brackets. Let's see what, and each line should be justified. So in the first justification should justify this whole thing. Why W is equal to VB? Do I have it in my givens? Well, I have this, which is almost the same. So let's say that we should accept this. I emphasize the almost the same, but okay. Why is it not exactly the same? Because actually what I have is VB equals W, and what I want is W is equal to VB. But let's suppose that this whole configuration here can take care of some simple things for us. Like, if you have A equals B, I consider that B is equal to A. We have to discuss this about equality, but not yet. So, what do I need to justify here? Be careful, this is a common mistake. There's not an implicit W here that I'm not writing in order to save the planet by saving ink. The second line is a statement that this guy does this with that guy. And the last thing is that this guy does this with this guy. It's not like implicit W's here, okay? So here I justified the verb of the line, and here I have to justify the verb of the line. Why is this guy equal to this guy? And if I look closely, I observe that actually what I'm substituting is V with this. So essentially I need to justify why V is equal to UA, and somebody can tell me the name of this? HA, thank you. And the last thing, if I look closely again, it's not like I'm substituting a simple part with another part. I'm substituting the whole thing, so I need to justify why the whole expression is equal to this expression. And this is like an axiom I have for the integers, that multiplication is associative. So here I haven't given you a name for this, but might be something like multiplication is associative, or I don't know what. Okay? And some further details maybe. Okay? Yeah.
Στο δεύτερο βήμα δεν κάνεις substitution με κάποιο τρόπο.
Yes. So some things are taken care, seem like magic here in computation. Essentially, it's like things like reflexivity, transitivity, symmetry, and substitution for equality. So the idea is that this mini environment should take care of these things. Essentially, this should translate to various uses of equality, which I don't have yet, and I just want to skip this part for now. Okay, so essentially, this is like a macro or a convenience or a syntactic sugar that is extremely convenient. We like to write things like that. We're used to writing things like that, and it would be like a pain in the ass if you write since A equals B, then B is equal to A, and then since from symmetry, and then from transitivity, A is equal to B and B is equal to C, therefore A is equal to C. So pretty much we have a nice environment that does these things for us, but we need to justify them when we get to this part. For the time being, I want to know that this proof is more or less followable, because I want to start. Okay, somebody objects strongly to this proof. Criticizing some things and start thinking some things in a different way. Stelios, yes.
So all these lines are of type command. All these are commands.
These things, or these things.
These things.
The big ones. Yes. Pretty much, we are going to say that a proof script, let's call it like that. Each line is a command, or maybe it's like this first line here, that it's like 3 commands in disguise. And actually, this thing also is like of similar nature. If you translate the commands, you will have a bunch of commands that you don't want to see, but they are commands. And just small parenthesis, you should have like comments in your proof as to help your reader and yourself understand where you are at and what you're doing and all. It's a good balance of how many comments. It doesn't make sense to say, now I am about to use that u divides v, and now I will use that. Okay, we can see that. But essentially, when you want to say how you figure out this thing, you should write. So it's a mix. This will be comments. Let's call them comments. Yeah, but what was your point?
I'm still confused as to what the command is on the very first line. The since to.
This?
No, the one.
This one?
Yes.
Okay, yeah, so I didn't mention that. Thank you for the answer. And since we will have a break, probably this will be the last thing that I will say. This more or less is like I'm implying that if you use this with the only way you can use it, or with an obvious way that you can use it, consult how to use stuff. If you use it, you will obtain this. So it's like a command. If I write this, okay. Since, let's say something, let's call it P, then some Q. If this command is to be executable, it should be the case that the use of P gives me Q. And the effect of this command is, okay, then give me Q. Okay, it's like how I want to say use stuff. But it gets very tiresome to write stuff like that. And I will also introduce a convention that if I say hence blah blah, it means that I'm using what I just wrote. So if I say hence R here, essentially it means use the thing you just gained, which is Q in this case, and obtain R. I'm just trying here to mimic maybe how we would write a proof as a human. We say these things, since this, use that. Essentially, these are not essential commands. The commands are only this and these. So this is more or less to make it sound a bit more human. Does that make some sense? More or less?
It does make sense in general, but in this specific example, and the way we had to treat it before, you put the 2, the parenthesis 2, it didn't really mean something. Before it was since
Okay.
u divides u, then
Let me translate this in an actual command, because this is like a mixture of command and comment. It's ugly, and I get that it's ugly. And here it should be like just let k, let k, such that this thing. And since, okay, and now to help someone understand which existential am I using? Because I have 2 existentials here, like I have this one and this one. I would maybe write something like, okay, I'm using, I don't know, what was its name? 2, maybe? And then I will say I'm using 3. Does that make some sense? Like I want to use this. It's ugly, and this is part of the point that I'm trying to make here. We need to pay attention to some things that usually we don't. And this will be the point of, we'll start appreciating what is sometimes called like constructive mathematics. And there is a lot of weird opinions and prejudices about the subject. So this will be what I'm going to discuss like after the break. And before the break, there are further questions. Yes, Manolis?
Yeah, I think the confusion maybe here is arising from the fact that it looks like we're having arguments and implication essentially. And
An implication?
it looks like we have an implication or an equivalence. Like it looks like we have the fact that u divides v is equivalent to
Oh, okay, so thank you very much about that. So this is why this is blue, okay?
It looks like we're using modus ponens essentially.
Yeah, okay, so it has nothing to do with that. I don't know if this was a confusion. Consider there's a big parenthesis here, okay? I'm just trying to remember what it means. My given here is not this thing. My given here is this thing, and I'm just remembering what does that mean.
Essentially, our given
So-
is the same as the other thing. It's as if we have the second thing in our given space.
Yeah, it's like my given is this, and I say, okay, remind me, what does that mean? Oh, it means this. So my given is this, or my given is this. That these 2 are interchangeable. I don't know if this helps, if your question had to do with that, but this is an important point. Maybe I should have written this parenthesis or explained it better. It would not make sense for this to be my given, because my givens here are objects or propositions, and this is not a proposition. This is just a judgment. It's just a translation. Okay. This thing means that. Okay. Yes. Final question before the break.
Πριν είπαμε ότι το since και τα λοιπά είναι ταυτολογία, επειδή είπαμε ότι...
I wrote the same thing twice here, right? Sorry, what is it? Since it was better before, right? Since u divides v, then u divides v. Look at that. It's the same thing.
Ναι. Και τώρα είπαμε ότι αυτή η εντολή είναι ισοδύναμη με το let k τάδε. Την από πάνω γραμμή δηλαδή.
Okay, you are... no, this thing? No, that was a mistake. Thank you again. This is the correct thing to do. What is the correct thing? Since... I have never done that. Okay.
Big below, like
Maybe I should... okay, thank you. This should be like in some other... Aha, yes, okay, thank you. It's here. So this should be here. Like this thing should replace this line, right?
Ναι, αυτό και...
Okay. Does that make sense? Yeah, thank you. Okay, a break and see you in a bit. So, there's a chance that I was not recording all this time, but I hope I was. We'll find out later on. So what has happened is like we have written something that's in the middle ground between how humans usually write things, but paying a lot of attention and kind of transforming it to look like programming, like commands and stuff like that. I'm making the point that if you read like proofs with this mentality, you can pretty much see this, like if you think of Euclidean geometry or something like that. So the first thing that I said it's a bit weird is like we have an obsession as if like mathematicians cannot give labels with any other thing other than numbers, and it becomes much more readable if I figure some better names for the things I want to refer to. I hope this is not objectable. I mean, why should I always have 1, 2, 3? From 3 and 5 and 8, it follows that, okay, and how should I label this? 16, because I counted all these things, number 16. It doesn't really help me. It's good to have labels, but this is like a communication kind of thing. One can say, okay, fine, this is not, I will not change the way I'm thinking about mathematics. It will only change the way I communicate it, and it's good because it's easier to communicate. I hope we can start doing that in our everyday mathematical activities. But there is something here that should irritate you, should make you like feel uncomfortable, because at some point I'm trying to find a givens table, pretty complete like this one. So if I look at the givens here, there is something that irritates me. And it should irritate you because, like, as mathematicians, we should have like some, I don't know, OCD or mathematical OCD or something like that. And if I look at the givens here, what type of things they are? Like, I look at this one. It's an integer, and I have a name for the integer. So it's a name, and what kind of thing it is. And this thing is an integer, and I have a name for the integer, and this is an integer, and this thing has nothing to do with that. Suddenly, here I have like objects and their types, typings, and here I have a proposition, right? I don't mean that I have the fact that this is a proposition, okay? This is not my given. My given is like an actual validity of a proposition. Just a second. So there's already something that's a bit weird here. My given, I cannot say my givens are like typings. I cannot say my givens are integers, objects, or whatever, not propositions. These three things look like propositions. These three things look like integers. And if I want to visualize this whole proof, what happened here, let's say I'm talking with, I don't know, Panos, and we're discussing this marvelous discovery of mine that if A divides B and B divides C, then A divides C, or something like that. So we have like the table on which we are looking at, and we are discussing those things, and what lives there are mathematical objects. Integers, some functions on the integers, some relations like, I don't know, the divides or whatever, and we communicate, and the whole proof takes place above the table, and the only things that are on the table that we can mess with them and do things with them, construct things with them, and operate on them, and all those things are like integers and functions on the integer and stuff like that. Namely, those things don't look like that. So when I say like here, since 2, or the better named this guy here, the 8a is not visible on my table. It's not an integer, and we're talking about theory of numbers. And the whole idea here that I'm trying to say that there's no reason to treat this as something different. It should be a mathematical object with the same rights as everybody else. It should be a first-class citizen of our discussion, not only the integers, but also facts about the integers. Okay, I will pause here. Questions or comments or whatever. Yes?
Αυτό οδηγεί στο ότι το V-typing είναι κάτι διαφορετικό από τα άλλα που έχουμε ή ότι τελικά είναι ίδιο.
So the question is, am I trying to argue that this should be of a different nature than this? And the idea is that no, all the givens should have, it's not the same rights in the sense that you can do exactly the same things. Like you can not add this proposition and that proposition to get a different proposition. Add like an addition, or you can multiply them. But they are visible objects on your table, and you can do things with them. What you can do with anything that's on your table is dictated by the type. Since these guys are integers, I can sum them and I can get a new integer, u plus v. Since this guy is a conjunction, I can do something on it, and this will be project left, and I can get a new proposition. And since this guy is a conjunction, I can do something on it, project on the right, and get a new proposition. And this operation, this discussion, this however you're going to call it, happens on the same table that I have all these other guys. They are parts of the proof. Okay? And the whole idea is, this is called like proof-relevant mathematics, which is an essential aspect. It also has a nickname, proof relevance, I will call it like that. I'm talking about proof relevance and mathematics as if humans matter, or as if people matter. Because the idea is that mathematics is a human activity. I want to communicate these things to you and you back to me and so forth. People matter. And now the proofs become actual mathematical objects. Because so far the proofs were on a different level. We were discussing this, and the actual proof is not visible for on my proving table. Okay, I like the table metaphor, but maybe you want to object to it, and that's fine. So, namely, I will visualize this like that. This thing, how did I call it? HA? Okay. So HA, so the big revelation is that these things will become like purple things. Sorry, not purple, orange things. And I will want names for them, and these names will be just as visible as the other names are. So here I will have like, let's call this HA. No, this was HA. This was HB. No, sorry, it was not HA and HB. Help me a bit, I'm losing my track here. This was called like, let's call them H1 and H2. It's not the best thing. Or like H left and H R, I don't know. And then later on, actually I had an HA and an HB. So I didn't copy the whole thing. So this was what? This was like UA equals V. And this was like VB equals W. And there is, and now I'm happy, like maybe I gave this a name H. And now I'm happy because all my givens have the same status, the same rights, they are citizens of the same class, let's call it like that. I'm not saying that they have the same type, okay? In the sense that these objects have the same type, but each line on my givens is of the same nature. I have an object of this type. And a big objection is that this is not a type. So let's make it a type. Or let's try to bridge the gap between what we understand by types and propositions. For the time being, what I will do is visualize this, each of these things that doesn't look like a type, this looks like propositions, visualize this as the type of all proofs of this proposition. So this thing, I can see it like as all possible proofs of this conjunction. And this thing, all possible proofs of these divides, and this, and so on and so forth. This is like all possible proofs of this thing. And the moment now that I say on my proof, instead of writing like that, I will write this now. Instead of writing something like let, or suppose, I would write something like this, right? Suppose, I don't know, let's say I used to write something like suppose U divides V. At some point I wrote this in my proof, right? And I called it like maybe I called it like HUV to remind me that it's something has to do with my U and my V, but just a name, just a label, okay? I can see this like that. I'm not supposing the proposition, and I'm labeling it to refer to it later. I'm saying like something like let HUV be an evidence or a proof or whatever you want to call it of this proposition. And now HUV is on my table of all mathematical objects. Now, I know that some of you have seen taking a course on mathematical logic, and maybe you object to it and say, no, what we've seen so far, like classically, proofs are also formal objects, mathematical objects, and be careful because you should not confuse the idea of, I mean, in mathematical logic, you do a bit of like, usually you see some kind of what is called a Hilbert-style proof system, and you define a set of formulas, and then you say that a sequence of formulas will be called a derivation or a proof if it does this and this and that. Okay, and this is indeed a mathematical object that you put on your table and you study, but this is a formal proof. Here, these are not formal proofs I'm talking about. These are the actual proofs that we're discussing. So when I'm discussing with like Nanopanos about this number theoretic thing, the moment I say the U on the table, I put this U on the table, I see it on my table, and the moment we say this thing, I see, where is it? Maybe this thing. I see this on the table. I see HL, it's visible on the table, I can do things with it. What I can do or cannot do with it is dictated by the type, so we have to learn what these types actually mean. Similarly for integers, I suppose I know for the integers. But eventually we will have to say, okay, if I have a proof of a conjunction, what can I do with it? How I can operate? Can I multiply it, or what I can do with it? Yes? No, it's not exactly like that. Like when you're doing mathematics, especially for those who have seen like a mathematical logic course, still when you're proving these things about the formal proofs, your arguments are not on the same table. Okay, you could say, I will study strings, or I will study a programming language, I will define it. It's now a formal object, and I'm arguing about it. Yes, so they don't, when I say, okay, every formula that has only this symbol, something happens, I don't know, to it, we are proving this thing not inside the formula. We are proving something about the formal proofs. The proof we are doing about them is not on the same level as those objects. When I say formal, I mean a formula, like a first order logic formula, like no, it hasn't anything to do with that. I think my example is better in the sense that I think we understand what's happening here. These things now, they used to be an oral thing, like we discuss it, we write it down maybe, I don't know, but they didn't live in the same table as these things. Even when you are studying formal proofs within a logical system, these behave like integers there, but the arguments you are making are again here. Okay? Forget the word formula maybe. Like formal, this is for people who have seen like a derivation or something like that. Sometimes they're called like that instead of proofs, the formal proofs. My point is that when I say proofs are visible within thing, I don't mean like some kind of formal proofs because I define the little system. I mean our actual arguments, like these things here. Okay, are we more or less... I will not convince you much with just like 45 minutes, but it's just a new way of thinking things, maybe for most of you or for some of you, that essentially what happens when I'm supposing something, I'm assuming that have a proof of this thing, and maybe there are different proofs, and I want to refer to this thing the same way I say, give me an integer, I will call it u, give me an integer, I will call it v, and u and v may be different integers. I may say, okay, give me a proof of this and a proof of that. Maybe I have on my hands the same proof, maybe not. Okay, so these are in the same status as these guys. All the propositions in my givens live. Okay, and essentially the objective when I try to prove something is to construct a proof of my goal. Okay, to construct an element of that, and someone might take this and use it. So the important thing is that when we prove something, essentially, we have constructed a proof, and when somebody wants to use our theorem, essentially, they are using our proof. And if I have two proofs on the theorem, maybe you say, I don't care, I just care that it's valid, but these two proofs can be very different when someone else is trying to use them. So you say, technically you should say, this is a proof of this theorem, and I can refer to it. And then if I want to use it and I have 5 proofs, it makes sense to say, okay, I want to use a third proof. Maybe, for example, you want to prove an existential, and there are various witnesses that exhibit this property, and depending on who you will choose, it will make a difference. Okay? Okay. So, questions? Yes, Manolis.
I don't. When we have like proof for a theorem or something, in order to make a difference, we kind of would have to extend it in order to prove like the theorem plus something else that we're interested in. Just the proof.
I don't want to use extended. I want to say use it. Think of a proof of a theorem just like a program. It's a program that convinces people of this thing, and there might be 2 or 3 different programs that do this thing, are convincing for some aspect. And when you want to create a new program, prove a new theorem, you might say, I want to import this proof of that theorem, or maybe that proof of that theorem.
So we don't just have access to like the thing as a black box, like we have this which is a proof
Okay,
of
so
an actual program.
usually what usually what mathematicians do is like say, okay, forget about what happened in the proof, just give me the statement and I can use it. And if you do that, you actually collapse all possible proofs of something, and all propositions, let's say, to like a true or false. You only care, I have proven this, so I can use it, yeah? Or I haven't proven it yet, or it's not, or maybe I have refuted it. But it will make a huge difference of like, if you start treating this thing as computations, as algorithms, it makes a difference like which algorithm will you use. So, and this has a bit with something to do with Areti said about the suggestion of how to prove an existential. So consider that I have given you, and we are about to discover that these things are not equivalent actually. Like I have given you an existential proof in the sense of, here is my witness, and here's the proof that my witness serves its purpose, satisfies this. And the alternative that Areti had suggested, I think it was Areti, I'm not sure. No? Okay, take it back. Maybe it was Maya. I will prove that it's impossible not to exist. Something like that. It's like, suppose that it's not, I think Areti mentioned something with disjunction, which is of the similar nature. So, if you forget what the proof is, you cannot do pretty much anything about it. But if you actually pay attention to the proof, one proof, maybe Euclid's proof of the existence of the greatest common divisor. Like, it gives you a way, you can execute it, and it gives you a way to compute the greatest common divisor of 2 numbers. And somebody who argued like, okay, let's suppose that there's no such thing as a greatest divisor, and we will find out that it's impossible. It's pretty useless if you actually want to do something with it. So the moment you want to say, maybe you want to actually find the greatest common divisor, and you want to say, okay, from theorem 5, let G be the greatest common divisor. And then I will ask you, wait a minute, how did you prove theorem 5? Did you actually give me a way to compute this, or did you say it's impossible not to exist? And we cannot confuse these two because it makes a difference. So the idea is, many times this whole thing, because of, I don't know, it's pretty much a social thing. Hilbert had become such a god in this thing, like an authority, that if Hilbert said this is nonsense, who was going to oppose Hilbert? And I said, I mistakenly referred to Brouwer as a student. Brouwer was not a student of Hilbert, but Brouwer had the courage, let's say, and the insight to oppose this thing, and there was a huge fight, and pretty much the thing that's very well known and passed from generations is like there's some weird thing that some people are doing, which is more restrictive, and we can not do the full things that we would like to do. Like Hilbert described it as like you are robbing a boxer of its gloves and things like that. And that was very nasty. The controversy between Brouwer and Hilbert was very, very ugly. And it's weird that Hilbert was actually pretty much dying. He was very old, and all his efforts were like to destroy the insight of Brouwer, and it's a pity. The bottom line is Hilbert did not understand what Brouwer was doing. Okay, and I hope that we can understand this and appreciate it. And the idea is that when you pay attention to certain details, and when you prove things with fewer axioms, with fewer assumptions, you have stronger theorems. This is something nobody would object. Independent of what your philosophical position is here, if I prove a theorem and I use like 5 assumptions, 5 axioms, and I prove it using only 3 of them, I have a stronger result. Even Hilbert should be able to accept this. So it's like an appeal to some kind of computational hygiene, maybe, or something like. Let's be careful. Let's not call things the same, because maybe at some point we will care of this subtle difference, and if we don't care, it's fine, because we can still do everything that Hilbert does. We're just being honest about it. We'll see this like in a more concrete example, because the main homework for the next time, when I will insist on you trying to do more homework and post them on Zulip, will be like I will list a bunch of logical tautologies, which classically people will say, okay, these are indeed equivalent, and let's prove them. And there is no argument like I did the truth table. I want a proof. And we'll find out that a lot of equivalencies like this, like, I don't know, something here, if and only if something there, are like halfway true. Like maybe one part is actually indeed is strong enough to conclude the other, but not the other way around. And I'm not going to tell you in advance which are which. So the point is that you will have a bunch of exercises like, okay, I will give you a silly example. The first one might be something like, let's prove that P or P. Sorry, that P implies P. Okay, probably we should be able to derive this. And I will sketch very quickly how to prove that. What will be the first line of my proof here? Manolis, yes? Suppose P, and if I want to I will write like that. Suppose I have a proof of P. Okay? This corresponds to the idea of suppose P, I agree, because Manolis made an ugly face here, and I get it. This is more natural. And now I'm saying, suppose I have a proof of P. Okay? It's just this idea that these are proof objects. Not proof objects, this is first-class citizens, I prefer to call it like that. Okay, and now what happens to my state? Now I have P and I need to prove P, and I pretty much say, okay, I'm done, because in my givens I have my goal, and that's it. Like use P, just P, or just P, I don't know how I should... P is already a proof of the thing I'm trying to prove. I have it. You wanted a proof, like of this thing, but you accepted to give me a proof of P. And now that I have a proof of P, I'm looking for what? For a proof of P. I already have it. It's completely silly, completely trivial. It's pretty much, it's like I'm defining the identity function for a type or for a set. You want something from A to A, okay, then give me a little x of A, take back the little x, that's it. It's like the identity function. And this pretty much means, I'm realizing now that I haven't discussed the interpretation of implication. So the idea, that's a good point to do, a good moment to do it. How do we understand implication? Because, let me see, is it really blank here? Where is the implication?
Is this like an axiom of logic that always P implies P?
No, this is a good question. Forget this idea that we are doing something and then we have some axioms of logic. The idea is that we're developing type theory, and itself has its own logic, let's say, built in some way. So it's not like set theory that I have the axioms of set theory and also some axioms, like maybe this or maybe that, I don't know, modus ponens or whatever, that allow me to do things. While here, type theory by itself is a logic, let's call it like that. So it's not, here are the axioms of logic and here is type theory, and use logic to investigate type theory. It's like, this is type theory, and by itself is, call it sufficient or strong, I don't know how you call it, to do all the things you want to do. And we will introduce new types and stuff like that, and the idea is to find a way to interpret logical propositions, mathematical propositions inside our types. Eventually, we will pretty much identify, it's not exactly like that, but we will pretty much think of types as propositions and propositions as types. And the proof of a proposition will be like a program of certain type. And in this sense, I will just give this as a teaser or as an irritator, I don't know. Usually people think like this is mathematics maybe, and like this is a computation or computer science, because we build it on top of that. We are kind of trying to invert the point of view here, like this is the computation, and upon it we can found mathematics. And there are computations that don't really correspond to mathematics. Like you may have I don't know, maybe Tetris is a computation if you want to think like that, or the number 5 doesn't really doesn't look like it corresponds to a theorem. We can find some connections. We will discuss this.
So here you accept P implies P because you built a function that returns P given P.
Pretty much this, but it's not like I accept it. It's I'm proving it from what I understand for this symbol to mean. So P implies P. By the meaning, the computational meaning is that it's a process that if you give it proofs of, it's better to discuss it in terms of P implies Q. Okay, much better. So the idea of P implies Q is this: given proofs of P, I give back proofs of Q. I can transform a proof of P into a proof of Q. If I can do that, I have a proof that P implies Q. So my proof will have to receive a proof of P, and now it's essential that it's in the same status. I mean, it's an actual object on my table, and I can. So like if I have this on my data, the point I'm trying to make, if this is, I have an H on my givens, since it's a function, I can apply it on arguments. So pretty much, I'm arguing that this thing will end up being something like this. It's a function that transforms elements of P to elements of Q. And if I visualize this P and big Q as proposition, it transforms proofs of the proposition P to proofs of the proposition Q. Yes, sorry.
Το suppose και το let
pretty much these things we are pretty much trying to, we're discovering maybe that there are connections between this thing, I haven't mentioned it yet, and this thing. Both of these things look like functions in a way. And usually, it's like the command I'm trying to capture is like, give me an argument. It's quite common to call this command actually intro, like I'm introducing something. So give me this, intro X, intro whatever. And the idea is that if your goal is this, you understand that you are attacking this goal. If your goal is this, you understand that you are attacking this thing. Essentially, we will see that we can get away with fewer of these things, but for the time being, I want to stick with these 7. They are like more common, more usable, well-known, intuitive maybe. Yes?
Να στοιχήσω λίγο Σωτήρη. Δεν ακολουθάμε κάποιο στάνταρ αξιωματικό σύστημα για να κάνουμε αποδείξεις, αλλά ακολουθάμε αυτό που λες Type-theoretic. Πώς σχετίζονται τα θεωρήματα που μπορούν να βγουν με το ένα και το άλλο? Όταν μπορεί να αποδείξεις με...
Okay, so I think the question like what you can prove, let's say, in set theory with logic and maybe with type theory. Pretty much, I mean, yeah. Okay, there are two different things that make a distinction, that are important to answer this. First is like if you are doing a constructive proof and you care about those things or not. Essentially, when you're doing type theory, at least in the background, whether you want it or not, the system will be constructive, almost always. But you can say, I don't care about that, and that's fine. It just means that you collapse all proofs, essentially, or that you end up, instead of proving like something like P, you end up proving not P. And if you think they are the same, nothing is lost. You just say, okay, I will do this. So, but this has to do with constructive, not constructive, and somebody can do like constructive mathematics not based on type theory, like constructive mathematics based on set theory. This is a constructive versus non-constructive aspect. The other aspect is like, you could say like if this foundation is, I can prove more things than the other foundation, I can define more things, and vice versa. Usually what happens, like it's like a bad criterion to say, to compare foundations in the sense that this, pretty much if you take your favorite foundation A and my favorite foundation B, probably I can build your foundations in my foundation and vice versa. So it's not really a point that I can define things that you cannot. Since I can encode, let's say, set theory here, anything you can do, I can do. And since you can encode type theory in set theory, anything you can do, and anything I can do, you can do. It's quite different, like the nature and the philosophy and the way you are doing it, and it's extremely different if you try to implement it in a computer. Like if you try to have a proof assistant based on set theory, and like there are some, like Mizar is the most famous one, I think. You run into it's really complicated. While if you do it on type theory, pretty much you get for free all those tools from programming languages and typing system for programs. It's way more natural. You end up with a better system. So you can compare foundations in the sense like it's more useful to me, but it will not be in the sense that I have this theorem here and not there. And the same way that you can tweak set theory and say I will accept a limited choice principle for this one. So completely the thing changed. In type theory, you can say, okay, I want to have this rule or not have this rule. So you can tweak it a bit, both things. Yes?
Εντάξει, οκ, αλλά είναι σημαντικές οι λεπτότερες λεπτομέρειες του κάθε μαθηματικού μοντέλου. Και όταν κάνουμε όλα τα κατασκευαστικά, πολλά πράγματα τα αξιώματα της επιλογής ακούγονται από πλούστερα σχόλια.
Yeah, I think it's a bit too early to get in all these details. For the time being, I would like to appreciate a shift in the change of point of view of how we look things. And for me, the crucial thing here is like this proof relevance. Like I have these things. Sorry, I don't remember why I did that. Here. So these things are on the same table as these things. If we get this part, I think I can proceed and open further discussions in Zulip, right? Yeah, but that's where we should do that. So to sum up, no, I'm not here yet. Okay, so how would this prove? Okay, so I proved this thing. So I get the right to say that I believe this, that P implies P, and that's good news. Okay, so here's a kind of more tricky one. P or Q implies Q or P. Sorry, I read this implies, it's not implies, okay? This is like on a different level. This is the game board. From this, infer that. Write a proof of this, knowing this, okay? So, any suggestion how you would do that? I could call that like commutativity of disjunction, and maybe just to see if I learned how to write how to attack implications, I could start like that, but the first line here would essentially do exactly what I did before. Like, what would the first line here be? Yes, Manolis? Suppose I have a proof of P or Q, which you will call how? Pick a name. Manolis. Somebody said Manolis? What, sorry? Maybe. Okay, I don't know. I will not have a strong opinion on this name. Let's call it like H or I don't know, or D for disjunction. Okay, so you have a little d here of disjunction. Okay, suppose this. But for the time being, actually, we can get away with this. At some point, we'll need to refer to these names because we'll need to do things to these things. But for the time being, let's say I could skip this. Suppose, right, informally, let's say. Okay, and now my goal is disjunction, and my given is a disjunction. What do I do? Okay, who wants to attack the goal? Nobody? Who wants to use the given? Okay, for a good idea. Let's attack the goal then. So I have to choose left or right. Okay, and since more of you prefer to use the goal than to attack to use the given than to attack the goal, I suppose you get what's the problem with this thing that I'm about to do. I will say, okay, left. I'm picking the left thing. So at this point, this was the state of my thing, and now that I picked the left, it means that I'm claiming that I can prove this. And if I sit back and watch the state that the chessboard I'm in, I cannot do the checkmate I want anymore. right? Because obviously I should not be able to infer Q if I only know P or Q. So I say, okay, that's a mistake. Let's take it back. And what should I do? Use the given, the disjunction. How do I use the disjunction? Yes?
Kind of split.
It's not, okay, technically it's a good word for that. The thing we call split, it was like attacking a conjunction. So I want to prove two things. Now it's a case analysis, right? I will look at the disjunction to say what is it made of. Is it a left thingy or is it a right thingy? So here I will do case, separate by cases. In cases, and I have to say which disjunction am I using to separate it in these two cases. By P or Q. So I have two cases to consider, case left and case right. What happens in case left? What is my board here? Somebody? Yes, Manolis? Sorry? Wait, in my givens, actually P or Q has become P.
You asked for the goal.
Okay, probably, but that was my mistake. Okay, so yes, I meant to say the board, the whole thing. Okay, so here I want to prove that from P I can get P or Q. Yes, thank you. That's important. Q or P. And within this case, I have a new scope of proof. So if I introduce new things, it will not affect the other case. And the other case, which I have to do as well, I need from Q to infer Q or P. And now it's good news because now I can choose left or right appropriately. Okay, so I will not do any more proofs. The idea is you start writing these things, and eventually you will get stuck. I mean, if you try to prove all the things you learned in logic as laws, you will get stuck. Famously, you will not be able to prove this. When I write this symbol, I just mean do both things. Okay, I mean do this and do that. And also famously, you will not be able to prove P or not P. And also famously, maybe not so famously, I don't know, you will not be able to do the De Morgan laws. How should I write the De Morgan laws? Okay, maybe like not P or Q is derivable by and also is provable by and also proves not P and not Q. And as I said, most of these times, one of the two directions you'll make it, the other one you get stuck and you start appreciating that, okay, maybe it cannot be done. Okay, yes? I don't know, check the recording. From the system we're making here, right? Okay, you will not be able to prove these things, and you will appreciate that maybe they are not exactly equivalent. Maybe one is stronger than the other. That's the idea. Okay.
Αυτό είχα ρωτήσει. Αυτό νομίζω νωρίτερα. Ότι υπάρχουν. Αυτά δεν μπορούν να αποδειχθούν από αυτό το σύστημα.
Like, for example, this thing?
Ναι.
Okay. Yes, but on the other hand, you can say, okay, I will add a new rule to my system. Okay, and this is like a good moment, and I have 8 minutes, and I think I can do it in 8 minutes, to talk a bit about the law of excluded middle. So maybe you've heard about it with this name. It's famously called law. I don't remember how it's called in Greek. Αρχή αποκλεισμού του τρίτου. Okay. Usually its language speaks middle. There's no middle ground or there's no third option. Okay. So this is the principle, if you want to call it like that for each proposition P, we have this P or not P. So the interpretation we have on this junction is as follows. If I claim that I know this junction, I know if it's a left something or if it's a right something. And if it's a left something, it means I have a proof of that. And if it's a right something, it means I have a proof of this. So with this interpretation, it doesn't make sense to expect this to be valid because pick your favorite open problem and I'm sure that you don't have a proof either of the left thing or of the right thing. In this sense, I might say true sometimes. In this sense, I will redefine maybe or introduce this kind of judgment. When I say A is true, what I will mean for this conversation means I have a proof of A. This is what this thing will mean. So in this sense, it's not the case that for any P, I have a proof of P or not P because there are open problems, okay? Pick your favorite one and this should be convincing. Now, the important thing to understand is that we are not refuting any particular instance of this. So it is not the case that we are saying that for some P, I can say that it's not the case that P or not P. Even worse or even better, we are able to prove, to refute this. We'll say, no, this is nonsense. For any P, it is the case that this negation is valid. Essentially, I'm saying that we will prove it's not the case that you can refute this. And now maybe I'm beginning to lose you. And I hope that I will not, and I hope that I have enough minutes to convince you about this. So this is a nice proof. Usually the first time you see this, you are able to follow line by line and say, yes, makes sense. But then you end the proof and you say, okay, what just happened? It's a bit weird. So let's try to prove this. And your first objection is we have no idea how to prove negation because I haven't mentioned anything about negation. So this is a plot twist. Just to give me a minute, I think I will send you to Zulip for this and you will simply disappear. But you should do that. So there is a plot twist here. I told you that these will be the 7 primitive things. And then I told you I'm not lying because I emphasized there will be 7. And for the time being, there will be 7. And you can imagine that silly stuff like that, do not need their own line on this table. Can somebody help me define this? I mean, it's quite simple. If I write this, what should this thing mean? Areti? Yes. Exactly. Okay. So this would be like P implies Q, and Q implies P, which means that thankfully I don't have to figure out new ways to use this thing and what it means to prove this thing. This thing just means this. Okay. So it's not primitive. I defined it in terms of other things, and I'm happy that I don't have to learn tons of stuff to prove stuff. There will be only 7 and 7, like 14 stuff. Even fewer in the future. Surprising. Okay, it's not surprisingly that this is also defined in a similar way. Difficult exercise for home, but surprisingly, then this thing will not be primitive. So I will need to define it in terms of something else. But if I look what I have here, I have nothing that expresses anything false or negative or whatever. So I definitely need something new and primitive thingy. And this will be what's called a falsum sometimes, or false, or falsehood, or boom, or bottom. I don't know how you want to call it. The idea is, first, crucial observation, that it's not a binary thing. It's not a unary thing. It's a zero nullary thing. It's already a proposition. By itself, it expresses the absurdity, the impossible, the falsehood. It's not the case, okay? It's a proposition that's trivially false. And therefore, this means that you should not be able to prove it. There are no special commands to attack this thing because it expresses the impossibility. If I had ways to prove this, it would not deserve this name, okay? And the way I'm using this is I can explode the whole, okay, this is a metaphor, but I can explode the whole world. You have given me like an atomic bomb and I want to kill this monster, I just explode the world, everything dies. Because everything, okay, this is a bit of silly metaphor, but every time that you try to prove something, the idea is that you want to convince someone that in case all those things happen, you can get there. And if you manage to get this thing among those things, you already know that you won this game because you're in an impossible situation. So there's nothing left to be done. This is called the principle of explosion. Maybe you've seen it, but the idea is if in my givens I manage an absurd thing, we don't have anything else to talk about because all this time I'm trying to convince you that if all those things happen, then you have to accept that thing. And I managed to get that there's no way that all those things are happening. So I win this game. Like maybe, what's a good name for that? Not trivially, but vacuously, maybe, something like that. Okay, it's called the principle of explosion. It's not a weird, like, principle of some weird cult or something. This is logically, classically also accepted. So if you think I'm trying to get you more things, weird things to accept, it's not the case. So finally, we get to see here how, where was I? What the negation means. At some point, I'm trying to write here to define negation in terms of, okay, here. So finally, I can define the negation of something to mean that if you, from this something, the impossible happens. So this thing will be defined as P implies bottom. So every time you see a negation of something, I don't know, maybe this thing, this is actually what race of thing, what kind of proposition? It's an implication. This means that P or Q implies boom, implies bottom, implies falsehood. Okay? Is that reasonable for a translation of it is not the case that P? I'm translating that if P, then it's the end of the world. It's impossible, it's absurdity, the absurd follows. So when I say to refute P, I will mean to prove not P. And when I say not P, I mean that...
Do you need the def notation there in the negation?
Yes, I left it as implicit. I'm defining this to mean that thing. Thank you. It's like up to now this symbol, I will consider the symbol meant nothing, and now I'm defining this in terms of implication and in terms of the bottom, the boom sign. Yes?
Εφόσον το bottom δεν έχει κάποιο προαπαιτούμενο για να αποδειχθεί και υπάρχει μόνο του, το να πούμε ότι P implies bottom, πώς προχωράει μετά στην απόδειξη?
Okay, good question. Anytime that you see this, from what I said, maybe you should say, okay, I should give up, I cannot do it. But there is one way to actually do this if you explode the world, right? So if you manage to get this thing on your givens as well, you can still end the proof. So if I have something like, I have an integer, and from this only in this context, I want to explode the world, probably I'm not going to do it. But maybe if in my data I also have something like, I don't know, 0 equals 1, and further other stuff, maybe now I can win this game, because maybe working on my data, I will get this thing on my givens, I will say perfect, I explore the world, I'm done. So this is pretty much the only way I will be able to prove something if my goal is this. There are no special commands to do this, but there is this atomic bomb thing that if I have it, I can use it to prove anything that's on my goal, including the absurdity. Okay, so it's a bit late. And I think I don't have time, yeah, definitely don't have time to do this. So actually, try to do this. I just want to unfold a bit the definition as a first step. Remember, this is a negation of something. So this means, I will color this, so this means that the blue thing implies boom as a first step. So that's the blue thing. The blue thing, and be careful with parentheses, implies boom. And now translate it furthermore if you like, or maybe you want to suppose it so that you get it here. But the whole point is that this can be further translated. And now the blue thing is what? Is that the orange thing implies boom. So if I fully unfold the negations, this becomes this. P or not P. And I said fully and I realize I'm being dishonest. Be careful of the parentheses here. So you could also do that. P or P implies boom, and all this thing implies boom. My advice is only unfold as much as you need at this moment. It doesn't make sense to take this and translate it like that, because as soon as I'm here, I can already attack the implication and suppose this and get it on the other way. So like, don't unfold everything because it will become unreadable and you will not be able to reason and understand what you're doing. We like definitions. So we end the thing here, and I hope I see more things happening in Zulip.